we're going to start the first chapter of operations. So I've spread this out over a few days, but my goal in that is to give you guys ample time to study. So you will have to study. Do your workbook, do the quizzes, the practice tests, do all of those. What is your role in operations?
To contain the hazardous material, defensive operations.
Defensive, yes. And so protecting life and property with very limited circumstances where we will come in contact. So defensive operations, not offensive, that's going to be at a tech level. And so what are some of those things that you might have to do?
There's a spell stopping.
Potentially, yeah. We can do things, set up. We'll talk about it in later chapters, but yeah, divert the spill or contain the spill, things like that. Might have to assist with decon of responders. And as we talked about, maybe if we can safely do it, rescuing victims, suppressing workers. So in order to protect life and property, you're gonna have to understand the material. That's good. If you don't have your ERG, go ahead and grab one. And you can kind of use it as we go throughout the day. Yeah, we're just starting. Okay.
Did panic yawn.
You say panic yawn?
Panic yawn.
Yeah. Okay, here is this is a short video. Be thinking about this if you were called to this incident. So I'll read it. The truck driver stopped at a truck stop, saw that his tank was leaking and the pressure inside the tank. Okay, looking at this, what do you think is in there? Maybe. Okay, so it's got rings on it. Corrosive. So he had stopped and he noticed that it was leaking, and we don't. When does a hazardous material become a hazardous material? Isn't it controlled or uncontained? Yeah. Okay. So it's a problem, right? So he's gonna call for help. That help probably could be us.
I think we're gonna do this. He's wanting to get out of here. And Rick goes out. Okay, if he's wanting to get out. Somebody just hit us up and said, I wanna get out here. Yeah, we need to get out here. Now, I told them to get going. If they wanna go out, it's what he says, nobody else does. See, they're wanting out of here now. They're telling them to keep going, so I think they got room.
So they did have a firefighter injury. He was burned. It was coming in and paying a fine because they had not properly shipped the material. Okay, so you guys are dispatched this. What do you want to know while you're in route or on arrival?
I think we're gonna do that.
What are some things you're going to want to know?
You're looking for your type of materials or your UN number.
Okay, so you want to know what it is, and once you know what it is, what else do you want to know?
There's victims.
What's that?
Victims.
Victims, good.
What's it doing? Like, is it smoking? Is it? Like,
Okay,
is anyone passing out?
what else?
Once you know the material, the initial isolation.
Awesome, good. So we're gonna find out what it is, and then we're gonna use our ERG probably to determine what actions we're gonna take. So things like isolation, evacuation. And we also want to know how best to mitigate it, right? So some things behave differently and react differently with water. Some things are flammable. And so it's really important to know those things when we're called to assist, because we don't want to make the problem worse. Excuse me, sorry about that. What operations levels do. We're gonna talk about physical properties. Chemical properties. We touched on this, the GEVMO. Touched on that in awareness. And then we're gonna hit on size up at different HazMat incidents. Okay, so our responsibility is to protect life and environment and property. So protecting nearby persons, so we'll look at, is it best to evacuate, is it best to shelter in place? What actions we need to take, and if we can contain the release from a safe distance, we'll do that, and then certainly want to prevent exposures. We talked about it first, you want to know what you're dealing with. And in the next few chapters, we're going to kind of understand and learn how different materials behave and their associated hazards. And that will start that process of implementing the response. Okay, so just to recap, what are your roles?
To protect by the environment and property.
In a defensive position for the most part. Okay. Identify the physical properties that can help you identify hazards. The physical and chemical properties will determine how it behaves, the mechanism of harm, how it will behave in its environment, and then also what will it do, like if it's in a container or tries to get out of that container. What are some of our resources, going back to your awareness, what are some of the tools you were given? ERG, good, that's in all our trucks, it'll be available, what else?
On monitoring.
Monitoring devices. That's gonna put us at a pretty high risk, so maybe we'll go to other things first.
Knowledge of like containers, basic containers,
Identifying, being able to identify containers, good.
incident plans,
Pre-incident planning, good.
occupancy types.
What else?
Our
What
census,
Census, okay. Any apps or anything?
Okay, wiser.
Wiser, good. How about anybody we could ask? Sure. So if it's the, a train, we're gonna ask the conductor. If it's the truck, we're gonna ask the driver. At a facility, we're gonna ask for the SBS. Okay. So knowing what we're dealing with will give us an idea of how that incident is going to progress. You'll want to know how that material is going to behave at different pressures and temperatures. If how it's going to react if it's mixed with other materials. You want to know state of matter. What are your states of matter? All of it. Yes, we want to know its melting point, freezing point, and sublimation, vapor pressure, boiling point, specific gravity, vapor density. Things that play into that are molecular weight, particle size, persistence and viscosity, solubility, miscibility. We'll talk about all of these. Solid, liquid, gas. I don't think we need to hit on that anymore. You guys are over that. So what do we know about a solid? Where's a solid gonna go?
Nowhere.
It's gonna stay where it is for the most part unless a force is applied upon it. How about a liquid? Yeah. Might cool in low-lying areas. Go ahead.
So for the solid, depending on, I guess the size of the particle would determine how far it spreads.
Yeah, it could. Yeah, so you have like small particles, and I've got a video I'll show you guys later. Yeah, it can spread, it can become airborne. It's still solid, but it has some other hazards with it. And then how about a gas? What's that? Yeah, that's quite a bit harder to contain. So liquid will maintain the shape of the container, and the container could be like a stream or like a ditch or anything, whatever it follows. We'll consider that. It takes the shape of the things around it, where gas kind of just goes all over. So if you think you've got maybe that's not a good example. I can say, so you put liquid on a slide, what's gonna happen? Goes down the slide, okay? You put gas on a slide, it's not gonna stay. Yeah. So solids are the least mobile. Liquids can be mobile depending on the properties. So you think some liquids move better than others. And the physical state might change if the temperature changes. What do you think about? Is ice going to stay a solid if you bring it out in room temperature? Incidents involving gases are probably going to be the most dangerous. Some have an odor and some don't. They can be toxic, they can be corrosive, they can be flammable, might be under high pressure. Some could be extremely cold, or when they come out of its container into the air, you have a great expansion ratio. So we talked about gas having an undefined shape and volume, and if uncontained, they continue to expand. They'll be difficult to detect. You know, things like solids and liquids, we can pretty much see those where gases may not. And then if you have a gas leak in a building, I mean, if you look at this picture, that is going all over, really can't say definitively where it's gonna go. Yeah, so it talks about it's going to be pretty darn near impossible to contain this gas. So this is you show up on that and you're thinking, oh, I'm just going to contain that. Well, how are you going to do that? Now, what if this was a liquid? A lot easier, and then if it's a solid, but it's probably not going to go anyway. Now, if you have a compressed gas, what's going to happen?
Go faster.
Yep. It's squished down tight, and yep. Whatever the release is, if it's a leak or an explosion, and then it just goes everywhere. So, and then we also look at weather factors. Is it going to be carried by wind? You might have to have. We have 4 gas monitors that we can use. There's just a handful that we can detect with it. Where technicians have more specialized equipment that can detect more things. Don't rely on your smell, your sense of smell, to determine if you have a hazardous material or hazardous gas. Because once you smell something, what does that mean?
You're
You've been
supposed-
exposed, yep. To know this, that materials under pressure. Or temperatures higher or lower than the ambient temperature, they could change their state very quickly if released. And then think about the expansion. That's gonna be a pretty big deal when we're thinking about how to mitigate the incident. So if you have something that like looking at all your information from it, it's gonna expand, but it's only gonna be maybe 100 yards. Versus something we know it expands, it's gonna be a mile. It's pretty significant difference in how we respond to it. Remember this, as gases expand, they can displace the oxygen. What's the sixth? Toxic? Okay, what's an 8? Okay, and you see the pictograms? So this one has 2 hazards, right? It's an inhalation hazard and it's also corrosive, so if you get it on your skin, it's gonna eat through your skin. All right, liquids, typically we can see liquids, so it makes them a little bit easier to detect using our sight. And you can tell a lot easier with a liquid, like how far it's spread versus a gas. A lot of times, we're gonna need gravity or another mode. So like here, if it gets in the waterway, that's gonna be a problem because it's gonna take it a long distance. Typically, they're gonna pool, they're gonna go with gravity. Excuse me, could be a splash or contact. That's right. So here are some of the challenges of liquids. Contact hazard, inhalation, they can be flammable, corrosive, toxic. And then the vapors from the liquids will behave a lot like gases. And those vapors can be flammable, corrosive, or toxic. Solids. Like I said, they're not going to move unless there's a force placed upon them. Particle size influences their behavior. So one of the is this a problem? Yeah, what's happening to this guy? So he's in there and he's trapped and he's not going to be able to breathe because of the force placed on him. He's stuck. There's a lot of things that's going to happen. We need to be able to get him out of there. What about these small combustible particles? You guys heard of like grain explosions? I've got a couple videos I'm going to show you guys. Pretty easy to see a solid, unless they're microscopic or smaller than our eyes can detect. Do you guys know what sublimation is? Okay, show you a video on that. It's when it bypasses the liquid state, it goes from a solid right into a gas. So like dry ice, that doesn't turn into liquid. It just goes right from that chunk of the dry ice into the gas. The solids are going to be easier to contain and confine. Really, they're for the most part, with some exceptions, they're going to stay put. Here's this video on sublimation.
Different types of matter react differently to different amounts of energy. So remember, we're thinking of energy as being heat. And here I have another solid, but it's even colder than my ice. This is 109 degrees below zero. This is dry ice. Dry ice is actually made out of different molecules. These molecules are made out of carbon dioxide. So we have 1 carbon atom and 2 oxygen atoms. And in its solid form, it's really, really cold. Those molecules are really close together. But as we bring it out into this room, which is a lot warmer than that dry ice, those molecules heat up so rapidly that they just skip the liquid form and they go straight to the gas. So that's a process called sublimation. It's a phase change. So we're going from one phase of matter, a solid, to a liquid because we're giving it a lot of energy. It's happening really, really fast. And we're skipping that liquid altogether.
I've got another video. Actually, I've got two videos right here.
Take a look at this video. See anything that seems dangerous to you? For most people, the answer would probably be no. It's just a bunch of people having fun, celebrating a tradition. But to a trained eye, there is in fact a fire and explosion risk present here. It's the dust. Now, while I wasn't able to find any records of fires or explosions resulting from Holi, the Hindu festival seen here, in which people throw clouds of dust, usually cornstarch dyed with bright colors, into the air and onto their faces and bodies, there was a catastrophic incident that occurred in Taiwan in 2015 at a party inspired by Holi. So what's going on here? How can dust or powder catch fire or explode? And most importantly, how can we stop that from happening? Welcome to Learn Something New by NFPA Journal. Each year, hundreds of combustible dust fires and explosions occur around the world. In the US alone, there were over 200 reported in 2019. Just a couple of weeks ago, 3 people died and several more were injured when potato starch powder exploded at a factory in Singapore. In the 2015 Taiwan incident, 15 people were killed and nearly 500 were injured. Combustible dusts run the gamut of materials. They include seemingly innocuous kitchen staples like flour, as well as byproducts of industrial processes like woodworking and metal manufacturing. So how do incidents occur? Well, 4 elements are needed to produce a dust flash fire, and only 1 more is needed to produce a dust explosion. Here's NFPA chemical engineer Alexander Ng with more insight.
So the dust explosion pentagon is an expansion of the fire triangle as it relates to dust. So the fire triangle starts with fuel, oxygen, and an ignition source. So if you have these 3 elements at the same time, you'll get a fire. So for example, if I have a pile of materials such as potato starch, and it's exposed to a sufficient ignition source, I can get a fire along the top of that pile of potato starch, because that's where the surface area of potato starch interacts with oxygen and can react. Now, if I take that same pile and disperse it in air, throw it up in the air, I get dispersion, and I can get a flash fire off of that. And now, if I take that pile, disperse it in a closed room, I get confinement, which allows pressure to build as the gases rapidly expand during the reaction. When you get an explosion, which is kind of a bursting of that confinement. So if you have a room, the room is the confining parameter. The pressure increases much greater than the room can handle, and the room bursts apart. And that's how you can kind of get a dust explosion.
So in other words, if you've got dust, oxygen in the air, and an ignition source, you can have a fire. If that dust becomes suspended in the air, you can have a flash fire. And if you add a confined or closed space to the mix, you can have an explosion. Fortunately, there are resources out there to prevent these kinds of incidents from happening. NFPA, for instance, has 4 standards related to combustible dust hazards. In general, they teach a concept known as the 3 C's. Contain, you want to contain your dust within process equipment. Capture, if you can't contain it, you want to capture it at the point of release. And clean, if you can't contain or capture it, clean it up as soon as possible. Read more from my interview with Alex in the link included in the description of this video. Thanks for watching. Did you know it's NFPA's 125th anniversary?
10 minutes.
At 7:15 PM on February 7th, 2008, a series of violent sugar dust explosions devastated the Imperial Sugar Refinery in Port Wentworth, Georgia, just outside Savannah. Explosions raced through the buildings, fueled by accumulations of combustible sugar dust and sugar that had spilled from equipment. Thick concrete floors heaved up, and brick walls were blown into stairwells and work areas, blocking many exit routes. Fires spread rapidly. 8 workers died at the scene. 6 more died later at a regional burn center. Dozens of others were injured. The plant's massive sugar packing buildings were a total loss.
The accident at Imperial Sugar was the deadliest industrial dust explosion in the United States in decades. It highlights the extremely serious nature of combustible dust hazards.
There were significant accumulations of sugar dust and spilled granulated sugar on surfaces throughout this facility. Conditions were set for a catastrophic accident.
Imperial Sugar's sprawling Port Wentworth complex began operations in 1917 and grew to become one of the largest sugar refining and packaging facilities in the U.S. Granulated sugar from the refinery was stored in 3 100-foot tall silos and then conveyed into packing buildings where it was packaged for distribution. Granulated sugar was also converted into specialty products, such as brown sugar and powdered sugar. Sugar was transported by a complex system of bucket elevators, screw conveyors, and conveyor belts. During this process, sugar spilled onto floors throughout the work area. In places, the spilled sugar was many inches deep. This sugar also contained fine particles, which became airborne. In addition, hammer mills were used to crush the granulated sugar into powdered sugar, creating even more dust. The machines were connected to a dust collection system, but it was undersized and in disrepair. And it was not connected to the bucket elevators and conveyors. Significant amounts of sugar dust escaped into the work areas. Workers routinely used compressed air to clean packaging machines, further dispersing sugar dust throughout the buildings. Over time, large amounts of dust accumulated on elevated, hard-to-clean surfaces, such as ducts, beams, and light fixtures. These surfaces were not cleaned often enough to always keep the dust below hazardous levels. In the tunnel beneath the sugar silos, granulated sugar flowed through chutes onto a long steel conveyor belt. From time to time, clumps of sugar would become stuck in one of the chutes, blocking the flow of sugar on the belt, spilling sugar onto the floor and releasing dust into the tunnel. But the tunnel was large and ventilated, so this airborne dust did not build up to explosive concentrations. However, in 2007, the company enclosed the conveyor belt with stainless steel panels to protect the sugar from possible contamination. The enclosure was not equipped with a dust collection system. As a consequence, sugar dust would now be trapped inside this enclosure. On February 7th, 2008, clumps of sugar were found blocking one of the discharge chutes. Sugar from the adjacent silo likely spilled off the moving belt. Dust likely accumulated to an explosive concentration inside the enclosure. At about 7:15 p.m., the sugar dust contacted a nearby ignition source, likely an overheated bearing, and exploded. This primary explosion blew apart the enclosure. Accumulated sugar was lofted and ignited by the advancing fireballs. The dust clouds fueled the chain reaction of secondary explosions, which swept through the building. Concrete floors buckled, releasing tons of granulated and powdered sugar into the flows. Emergency evacuation drills had not been conducted, and the explosions had cut the power to much of the interior lighting. In the maze of darkened and damaged stairwells and passageways, workers desperately tried to flee the growing inferno. CSV found that correspondence dating back to the late 1950s showed that plant managers in Port Wentworth were aware of the explosive nature of sugar dust and the danger of dust accumulations. As far back as 1961, a memo described a sugar dust explosion that heavily damaged the powdered sugar mill room.
Despite the longstanding awareness of the explosive nature of sugar dust, not enough was done to manage the hazard.
In 2006, the CSB issued a study of combustible dust, which called on OSHA to establish a comprehensive combustible dust standard based on the current standards of the National Fire Protection Association, or NFPA. In October 2007, OSHA began implementing a new national emphasis program to increase the enforcement of existing regulations related to combustible dust.
Imperial Sugar learned of the OSHA Combustible Dust National Emphasis Program 4 months before the devastating explosion at Fort Wentworth. But management did not act effectively to control the serious dust problem in the packing buildings.
Less than 2 months before the disaster, an internal inspection showed that many tons of sugar were still regularly spilling onto the floors. This provided much of the fuel for the massive secondary explosions and fires. The CSB found that over the years, the Port Wentworth facility periodically experienced small fires fueled by spilled sugar and accumulated dust on equipment, but none resulted in a sugar dust explosion that propagated through the plant. Investigators said that decades of operating without a catastrophic explosion may have lulled managers into complacency. In its report, the CSB issued the following recommendations to the Imperial Sugar Company. Apply NFPA standards to the design and operation of the rebuilt Port Wentworth facility. Develop and implement comprehensive combustible dust control, housekeeping, and training programs. Improve emergency evacuation policies and procedures.
Companies can go a long way to control combustible dust within their own facilities by following the existing recommendations of the National Fire Protection Association. But it is also time for a comprehensive federal standard on combustible dust.
In April 2009, OSHA announced plans to begin rulemaking on a combustible dust standard for general industry. In its final report on the Imperial Sugar accident, the CSB recommended that OSHA move forward expeditiously with the new standard.
Without regulation, enforcement, and education, workers will continue to be at risk from catastrophic dust explosions.
For further information, please visit csb.gov.
What standard matter is likely to be the most challenging and why?
Yes.
Yes, what?
Greatest mobility.
Yeah, it's mobile, you can't contain it. It's. And touch on these. Melting, I think we have a pretty good idea of that. Freezing, vaporization, condensation, sublimation, and deposition. That's a minute one. Maybe they're later on. Okay. Atmospheric pressure is the force per unit of area applied perpendicular to a surface. Standard temperature and atmospheric pressure, they're going to remain calm. The gases are going to remain calm, and they're not going to move a whole lot. Okay, what's vapor pressure? Well, let's, we got a here. I've got a sealed container. And I've got gasoline. All these vapors are coming off of the gasoline, right? That's the pressure, so it's the pressure of the vapors coming off of the gasoline, right? Now, what happens? And which one do you think is gonna have more pressure here? You think we're gonna have more pressure? Because what do gases do? They expand, yeah, and so which one's gonna expand more? The gas. Okay. Now, what happens if I apply heat? What's the boiling point of gasoline? It ranges, okay, we'll say like 100 degrees. Oops, that's 100 degrees. And then what is it for water? 212. Okay, so I've got my little flame here. That's a terrible drawing. Okay. So I'm applying heat to it. So what happens when we apply heat to something?
It expands.
Yeah, so this is gonna expand. So it's getting more and more and more pressure. And then, but I only have to heat this up to 100 degrees, right? Before we're really starting to cook. But I have to apply a lot more heat to water, right? To get that to expand. And you can't watch it because it won't boil, right? Okay. So does vapor pressure make sense? The amount of pressure coming off of the liquid, and different chemicals are gonna have different vapor pressures. And so we need to understand those so we can know how it's going to behave under different conditions. So like we talked about, the higher the temperature, the higher its vapor pressure will be, because as we put heat on it, it expands, okay? So that's more pressure in there. Okay. If you have a lower boiling point, so gasoline has a lower boiling point than water, so it's gonna have a higher pressure. Does that make sense? Okay. So we do have some substances that boil at room temperature. So does that affect your response or how things are gonna behave? Yeah, absolutely. So if it's 80 degrees out and we have something that boils at 68 degrees, that's a problem, right? Yeah. Units of vapor pressure. Oh, I thought I read that as one of the 2 units, but so if you look on page 132, there's a whole bunch of ways to label it. Okay, so what's boiling point? Without looking at the slide.
Point at which a liquid begins to transform into a gas.
So we use Fahrenheit here at so we calculated at sea level. Now I know that you're gonna have different boiling points at different pressures, right? So you guys ever get like a cake mix and it gives you like the high altitude instructions versus low altitude?
Wait, what, in high altitude? What's that? Bigger in high altitude or slower?
What do you think?
Lower.
Okay, your job is to find out on break and then come back and tell us. Okay, we talked about a levy. we did that in awareness. Do we need to touch on that again? Okay, what's happening in a levee? What does it stand for? Without looking at the slide.
Boiling liquid, expansive, vapor. Explosion.
Explosion, yep. Okay, so what's happened? We've got our. Take of bad things.
Isn't it where the container, heats up so much that it cannot exert the pressure?
Yeah, it can no longer. So we got a relief valve. I have to label things, my drawings are terrible. And then we got, I better make the fire red so you can know what it is. Okay, so this is heating this up and. Okay, so we've got our stuff in here. This is our liquid. Okay, so as we heat it up, what's happening?
It's turning into a gas.
Yeah, so now we have some vapors, they're just going nuts here. It's getting hotter and more vapors, and then pretty soon, like, I have nowhere else to go. Try and get out the relief valve, but there's so much gas expanding here that it pushes, and pretty soon, it's like on Thanksgiving, you guys eat so much that's nowhere else to go, you bust a button, or you break your zipper. Okay, so this guy's zipper is busted and boom. Okay. And we can look up bloody videos because those are always exciting to watch. Okay, what happens if that is, so we got gasoline in there? What happens if it's water?
It's boiling point higher.
The boiling point of water is, yeah. And so are we as worried? You got two tanks, you're like, I gotta fix one, which one do I pick first?
Yes.
Gasoline. Yeah. Hey, these make big moves. All right, specific gravity. I'm a little disappointed because some of the videos I put in here didn't transfer over, but when we go to break, I'll get some of those videos up. Okay, so, specific gravity, what is that?
Ratio of density, mass per volume of material to the density of the standard material.
Hey, what does that mean to you?
Oh,
There you go, the float does the same. So if it has a specific gravity of less than 1, what's it gonna do? It's gonna float. Okay, what happens if it's greater than 1? It's sink. Okay, and how does that affect our response?
Whether or not the liquid is flammable, it could determine whether we're gonna have a fire in hot water.
Yeah, definitely. So then we think about, okay, well, how are we gonna take care of that?
Which, I know there was a question, I forgot. Why is, materials less than 1, like, that flow, harder to extinguish?
So what do you think? So they're sitting on the top, and what might be happening? So say a lot of think about spills in, we've got oil or we've got gasoline, it puts that sheen. Okay, so that's sitting there on top. And what is happening to our stuff on top? That stuff. This is water. So think about. I think we have it in there's a couple things that are gonna go into play here. We might have some of this. Okay, or water's moving here. And that readily goes with it, it's light. But if we have something that sinks here. It's not gonna move as easily, so it sinks and heavier than water, so it's not gonna move as freely. Without a lot of force on it. Okay. Question. You have a flammable with material with a low boiling point? What's that?
Doesn't take as long.
Takes less heat. And we've got a lot of vapors. Could become a fire problem. Let's go ahead and take a 10-minute break. So come back at 10 after. And we can get going. And really look at those terms. We'll spend some time on this. How you determine vapor density. Going back to your chemistry class, you guys all had chemistry in high school or college. And do you remember like the molecular weight? It's specific to each element. We can go more into depth on that, but just know that the molecular weight helps determine the vapor density. We're on page 135. Excuse me. So vapor density is the weight of a given volume of pure vapor gas compared to the weight of an equal volume of dry air at the same temperature. So less than 1 means what? Nice. Greater than 1. Okay, so you have a gas leak of something that is greater than 1. Where's that gas gonna go?
Floor.
What's that?
The floor.
To the floor, yeah, low lying areas. Greater than 1. So what happens when you have something that's greater than 1? The gas is gonna go.
Oh, wait.
What's the one? What are some of the factors that influence it? So, what'd you say? Temperature. Okay, good. What else?
Like saturation in the air, so it feels like raining
Yeah.
or something.
Humidity. What else? Let's see if I can check that. Let's think of that.
Via atmospheric pressure too.
Topography. What's topography?
The lay of the land or the elevations.
So we have like canyons or mountains, even sometimes buildings can impact this way. All the unconfined vapor gases can mix with air with the lighter materials. So nice and dissipate. Okay, what's persistence?
Like the likelihood that a material will adhere to something.
What it is how long is it gonna stay in the environment? Okay. What do you think is gonna affect that? You draw 3 pictures. Okay. So, I have filled up 3 cups. This one's got gasoline. This one has molasses, this one has water. So I come back a week later. Don't do anything to it, just let it sit. What do you think's gonna do with that? What? So water's evaporated, so where do you think that, how low do you think that's? Over. What do you think back?
You said 1 week.
A week, yeah. Now we're there, we started here. Okay. What do you think the molasses is gonna be? Okay. What do you think the gas is gonna be? What's that?
Half.
It'll be more evaporated than water, so it'll be lower.
This is more persistent than water. Water is more persistent than gasoline. It's just the ability for how long it will stay in the environment. And that is affected by boiling point and vapor pressure. Here's what happens.
Yes.
So it's gonna turn in and it's gonna go away. Okay. Does that make sense? Okay. If it doesn't, tell me to slow down. Go ahead.
So an interesting thing, for example, I have gas cans at home. If you keep them sealed and they're pressurized, it doesn't evaporate as quickly.
Why is
Because they build up a higher atmospheric pressure and it keeps the gases, if it keeps the gases from escaping, then it keeps the liquid from, what's the term? Vaporizing. And coming off the liquid.
so it's significant, so nowhere for it to go? Okay, so persistence, ability to remain in the environment when unconfined. So molasses has higher persistence than water more so than gasoline. Not going to be referenced on an SDS typically. Okay, what's viscosity?
The malleability of a material.
Yeah, so it's like the thickness and flowability. Okay, so which one's going to work easier? This or my, I don't have water here. But what do you think?
Oh, water.
The water's gonna, yeah, because it's less viscous. So what is that? How does that play into our response?
Depending on the type of material, so say it's a liquid, how far that liquid's gonna travel versus another liquid, so water's gonna travel farther than molasses could be. Viscous.
It's more viscous, yeah. So we think we have a two semis were racing around the Fruit Loop and one carrying molasses tipped over. And one carrying ethanol tipped over. Okay. What's gonna happen? The molasses is gonna crawl out. We're like, okay, well, we'll stop that right there. And the other, so we have ethanol. What is that one gonna do? It's gonna go, yeah. So we have a bigger problem, right? So knowing what the behavior of your material, excuse me, plays into how we respond. So here it said the viscous materials tend to be more persistent, and so we see that. Makes sense, right? And have a lower vapor pressure. What happens if we heat these up?
Viscosity goes up.
So if I heat up my molasses, what happens? It becomes less viscous and it moves easier, right? How about for water? Same thing. Gasoline, because it has such a low boiling. It's gonna evaporate or vaporize. So it's something that's is more persistent. Is it going to have a lower or higher boiling point? Higher, okay. Lower or higher vapor pressure? You think about the vapors coming off of something. So lower or higher? Say it with confidence.
Lower.
Lower. Okay. SDS, what is that? So that's gonna tell us, gives us a lot of information, more so than the ERG, right? This is gonna be very specific to that chemical. Know that description of color and odor are subjective. So what you say smells like one thing could be different than what I say it smells like. Is it purple? Is it, have you guys seen the thing with the, I think it's like the dress, is the dress green or is it? You guys remember that?
Yes.
And then even different manufacturers have different variations, so. Remember, we don't want to rely on our sense of smell as the detecting hazardous materials. Natural gas, what does it smell like?
Raw eggs,
What's that?
raw eggs.
Rotten eggs? Okay. This is a trick question.
Nothing.
Natural gas is colorless and odorless. So in order to be able to detect it, they add mercaptan that makes it smell like rotten eggs. Why do they do that? Yeah, so the average person like, something smells bad in my house. Hey, unexpected odor? Something has escaped from its container. Thinking about somebody with gas. It's escaped from its container. Okay, you smell it, you're exposed. Again, sense of smell is not the most appropriate HazMat detector. Okay, material changes its appearance. What might this indicate?
A change in state of the matter.
Yeah, could be a change of state. What else could it be?
A reaction.
Hey, what does water soluble mean to you guys? What's that?
It makes it evolve.
How well does it mix with water? Why do we need to know that? Yeah, should we put water on it? Will water make the problem worse? Will it explode? Okay. What happens if you put water on the grease fire? Okay.
Pretty sure it puts it out.
I guess it depends on how much water. So, think about like hydrocarbons. They'll float initially and then start to sink. Yeah, got some videos on here. So the degradation, chemical reactions, exposure time will all affect the materials and change their characteristics. Miscibility. So, miscibility is two or more gases or two or more liquids to mix or to dissolve into each other. So our oil and rubbing alcohol, are those miscible? So materials that don't readily dissolve into each other are immiscible. So when we think about that, you have an oil spill. It's on the water, it's burning. Then what? Put more water on it. What's gonna happen?
It's gonna-
It's-
Spread out.
What's the difference between solubility and miscibility?
Whether or not it dissolves in water.
And miscibility is two or more gases or liquids that mix.
Which one was that? That was miscibility. Who more gases to me?
What's that?
What did you just say about?
Miscibility is two or more gases or liquids. That can mix. With or dissolve into each other. Want to know about your chemical properties? And want to know what's happening on a molecular level? And how things are going to be changing those chemical reactions. Reactivity of a substance. You're supposed to something out.
Guess the way it reacts with other chemicals. Yes.
So how it
What it
behaves,
does.
yeah. How likely is it to undergo a chemical reaction when it's mixed with other materials or even by itself? Some things are very highly reactive.
So would corrosives be an example of something that's highly reactive?
Potentially. I'll show you this video, it's about.
G'day everyone, my name's Ben and welcome back to the Fire Show. In this episode, we're going to be talking about magnesium. Now, why are we talking about magnesium? I don't hear you ask, because I'm actually standing in my garage and talking to a camera all by myself. Well, the reason why we're talking about magnesium is in a previous episode, I had to add an asterisk to one of the scenes where I was explaining that water doesn't break down and therefore it's actually really good to apply to fires. Now, this is the case in most fires. In fact, just about every fire we put water onto, water stays as H2O, puts the fire out, and then everything gets better. But in the case of magnesium, when we actually put the water on the fire actually breaks the water down into its base elements, being hydrogen and oxygen. And then it uses the oxygen from the water to actually further oxidize the fuel and then allow the magnesium to continue burning. Now, this is a really interesting problem because in many new cars, they actually contain magnesium components, which means that if we go to a vehicle fire, we can actually find that we're going to encounter magnesium. And as you can see here, when the firefighter applies water to magnesium, it actually really flares up. Now, the question is, what's actually going on here? And to answer that, we're going to do a little bit of an experiment where we're going to actually put some burning magnesium into water. Now, you can see here I've got the magnesium burning, and that's burning at a temperature of around about 3000 degrees Celsius. So it is very, very hot. And as I apply it to the water, what we can see is it doesn't just burn, it actually flares up. So what's happening is our water is being broken down into oxygen and hydrogen, and magnesium is using the oxygen from the water to further oxidize itself, and it's actually creating hydrogen, which could then burn in itself. So this raises the question, how can we actually put magnesium out? And we might just think, well, why don't we just hit it with carbon dioxide, which is a common fire extinguisher? And we actually encountered the same problem. So what I'm going to do is demonstrate this in another experiment. Now, you can see here that I'm adding my carbon dioxide to the beaker. And just to demonstrate that, what I'm going to do is actually light a little bit of rag with some petrol on it and just dump that into the carbon dioxide. And you'll quickly see that it quickly puts the fire out. However, when we do that with magnesium, what we actually see is the fire burns up. And this is because the magnesium is burning so hot that it's stealing the oxygen from the carbon dioxide. and therefore it's using that oxygen to further oxidize itself. Now, we're really starting to run out of options here. How are we going to put this magnesium out? Now, our third option is to cover it with sand or silicon dioxide. Now, I'm sure you can probably see where this one's going. If I only add a small amount of sand to our burning magnesium, we actually end up with the same problem. We can actually see that the magnesium is going to break our silicon dioxide down, and it's going to steal the oxygen from that molecule, and the magnesium can continue to burn. However, if we add enough of the sand, then we ended up with an oxidized layer on the outside of our magnesium, and the magnesium will go out. Now, I'm not suggesting we should actually turn up to a car fire and start throwing sand at it to try and put it out. That's obviously not a practical solution. And to be quite honest, if we just spray water at the magnesium, that's going to flare up and fully oxidize and go away. But it is important to note, and a quick Google search later actually showed that there have been firefighters injured from these magnesium flare-ups. So it's really important that when we're operating around vehicle fires, we keep our distance and make sure the fire is extinguished before we move into an area that can be considered dangerous. All right, well, that's it for this one. Thanks very much for watching, and I'll catch you in the next one. See ya.
I think we've covered the fire tetrahedron. Tell me again what it is. Okay. Heat.
Chemical reaction.
Okay. Activation and energy. What is that?
The amount of energy that's required to propagate a reaction.
Okay. So something that has a low activation energy, will that reaction happen easier or harder than something with a high activation energy? So we might have something that's light sensitive, heat sensitive, or shock sensitive. What do those things mean to you?
Those factors might make a material more reactive, or they might lower the, or they might add more energy into the material in a particular way that makes it more reactive.
So something is light sensitive, and start that reaction with what? With light, okay? Heat sensitive? What's shock sensitive?
Kinetic force.
Would a bullet be, well, I guess the primer? What would that be considered? Shock
So-
sensitive?
I think you have that, like the hammer comes down, hits it, so. I'm not sure, it might be a combination, so I'd have to look into that. I'm going to play this video, it's really short.
Whatever you do it for lesser at Harbor Freight.
Have you ever realised that all your life you've missed something that's kind of obvious? It doesn't have to be something important, it might just be really minor, but maybe someone says a word and your brain just kind of shifts a little as you realise that you've never thought of that. And it sort of feels like you should have. Last time I was making a video here at this explosives test facility, I just casually used the phrase high explosives because I think I assumed that high explosive just meant really, really explosive. So I was surprised when Steve, the explosives expert, pointed out that it is a technical term, and there is also low explosive. So the obvious thing to do was to demonstrate both.
Explosives are a mixture of a fuel and oxidizer. With low explosives, these are roughly mixed together. So they're particles of the two in close proximity. When a low explosive reacts, it's a thermal reaction. So it's heat traveling through the low explosive, causing the chemical reaction to occur. As it burns, the fuel and the oxidizer react together, producing lots of gas. That will just bleed off into the atmosphere as a big puff of smoke. In order to make a low explosive have a more violent reaction, you need to contain it. So you need to hold those gases in
and allow the gas pressure to build up until it bursts through the container that you've put it in. So you've got deflagration. It's just when you hold all the material in and the gas pressure, so the pressure builds up, which creates more heat, which makes the low explosive react even faster. It's a runaway reaction, and eventually the amount of gas produced overcomes the container engine and bursts it open, making a bang.
So a low explosive, just like any other fuel, is a thing that burns. It just burns quickly. The gas that it releases expands and builds up pressure, and then
A high explosive is also a mixture of a fuel and oxidizer. But it's not actually a mixture. It's down on the molecular level. So you've actually got the atoms of material in such close proximity that they're linked together within the molecule. And because they're so close together, they can react a whole lot faster. So rather than it being a thermal reaction that propagates through, it's actually a shockwave reaction. It's so fast that the shockwave can cause the chemical reaction to occur. The chemical reaction produces energy, which then sustains the shockwave, driving it on even faster. And that's why high explosives can actually go off at between 6 to 9,000 meters per second, which is pretty damn fast. Because high explosives require a shockwave to detonate properly, they can be exposed to heat and flame and will normally just burn away. In fact, you're actually allowed to have 50 kilos of high explosive in your car without having to put a hazard symbol up on your vehicle at all, because it's considered not to be that big a problem. Obviously, when the fire brigade see you pinned behind the steering wheel on your car at the side of the road and it's on fire, they're going to stand back and sell tickets rather than actually fighting the fire. So what you use is a detonator to give it a shockwave to get it going. A detonator itself is a little metal tube. Inside there's a small amount of secondary high explosive, a tiny amount of primary explosive, which is set off very easily, and then there's some sort of initiation system that will then set off that primary explosive. With electrical detonators, that's an electrical fuse head, and you pass a current through the fuse head. That produces a flash as it burns out. That sets off your primary explosive, which supplies a shockwave into your small amount of secondary explosive, which amplifies the effect. That then bigger shockwave then transfers into your main charge, which is then sufficient to set off the main block of explosive.
which means, weirdly, that high explosives can be safer than low explosives, despite the name. If there's an accident around a load of low explosives, they're all going to catch fire and go up. But around high explosives, as long as you keep the primaries separate, like you're supposed to, it takes a lot to make a high explosive detonate, or sometimes even to burn. That is until you want them to.
Stand by for firing. Firing now.
(141). These are, this is a table of reactive hazard alerts. So I'm gonna let you guys read those out loud. So we'll start with you, Russell. You don't have to read the whole thing, but what is the reactivity?
Okay, we got air reactivity.
So what's gonna happen?
Likely to react rapidly or violently with dry air, moist air may generate toxic and corrosive fumes upon exposure to air and may catch fire.
Okay, so give us a couple examples of those.
So we got nickel, zinc, titanium, and then metal, alkali metals such as sodium and magnesium.
Okay.
Yeah.
Okay, what's next?
Next we have decomposes at elevated temperatures above 120 degrees Celsius. Materials that are unstable and can readily decompose, that is, break down into simpler chemical components. Under rather mild conditions, where the temperature is less than 120 degrees Celsius or 248 Fahrenheit, the decomposition byproducts may be hazardous. Many of these materials may be stored under refrigeration to stabilize them. And that includes organic peroxides, peroxy decarbonates, and oxidizers.
Okay, what class are those?
Those are oxidizer class 5 and class 4.
All right. Allie.
Explosive, a material is synthesized or mixed deliberately to allow the very rapid release of chemical energy, also a chemical substance that is intrinsically unstable, liable to detonate under conditions that might reasonably be encouraged. So like dynamite, azide. Is nitroglycerin.
Mhm.
Yeah.
Alright. Okay. Highly flammable. Substances having a flash point of less than 100 Fahrenheit.
What's a flash point?
Flash point is the temperature at which a flammable substance will ignite but not sustain a reaction.
Exactly. Okay, go on.
And mixtures that include those substances, materials designated at highly flammable present and present an exceptional flammability hazard. And that they may suddenly and dangerously increase the intensity of a fire.
Okay, what are some examples?
Gasoline, acetone, pentane, ethanol, ethyl ether, toluene, toluene, methyl ethyl, MEK.
Okay,
Enter.
all right, Brandon.
Known catalytic activity. Substances that have been known to act as catalysts. Catalyst is a substance that increases the rate of a chemical reaction by reducing the reaction's activation energy. The catalyst itself is left unchanged prior to the reaction. Catalysts can increase the rate of reaction so much that reactions that are very slow and non-hazardous in the absence of a catalyst becomes hazardous and release heat or gases very quickly in the presence of a catalyst. Even small amounts of catalyst can cause a large increase in the reacting rate of the surrounding material. And they include transition metals, strong acids, strong bases, alumina, and iron.
Esteban.
Peroxidizable compound. Have to undergo spontaneous reaction with oxygen, component of air, at room temperature to form peroxides and other products. Ethers and aldehydes are particularly subject to peroxide formation. For example, peroxides can be formed when ethers and aldehydes react with radical forming impurities such as metals, and then react with oxygen in the air. The peroxides formed are dangerously explosive, especially when deposited as crystals after evaporation of the liquid portion of the ether or aldehyde. Examples are isopropyl ether, urine, acrylic acid, styrene, vinyl chloride, methyl isobutyl ketone, and ethers, hazardous ether.
Coral.
Yeah, polymerizable.
Okay. Capable of undergoing self-reactions that release energy. Some poly reactions generate a great deal of heat, which can further accelerate the poly reaction, a situation called thermal runaway. The products of poly reactions are generally less reactive than the starting materials. Examples: acrylic acid, butadiene, ethylene, styrene, and vinyl chlorine and epoxies.
Hydrofluoric. Substances that ignite instantly upon exposure to oxygen air. Generally, these materials are stored in solvents or inert atmospheres to prevent exposure to air. Many pyrofluoric materials are also water reactive and can produce heat and hazardous gases when they come in contact with water or humid air. These are extremely dangerous fire hazards that are generally stored under an inert atmosphere or in a solvent such as ether or kerosene that excludes air. And then the examples are barium alloy, something zinc.
Diethyl zinc?
Yeah.
And then the other one.
Cryptolonium. I don't know.
And then you got radioactive material. So spontaneously and continuously emitting ions or ionizing radiation. Radioactivity is not a chemical property, but a hazard that exists in addition to the chemical properties of a material. Examples would be radon and uranium. A redox reaction is provides oxygen necessary for the chemical reaction. So a stronger oxidizer would have a stronger reaction. So if you have higher concentrations of oxygen in the atmosphere, what's gonna happen to that fire?
It's gonna be more violent.
Hotter, faster, and brighter. So we think about that when responding. We talked about this in awareness about responding, or maybe it was our behavior, but places where there's oxygen, like medical facilities, or even in homes where people are on oxygen. So the reducing agent is the fuel, and then it combines with the oxygen, and then the energy is released. So some reducing agents or fuels are more volatile than others. I thought this was kind of a cool redox reaction in times of holidays.
So,
Gotta get
what are
that.
you gonna ask the wizard for, Pixel? Well, I'm not sure he's such a.
The music is pretty groovy. I thought it was kind of cool. So if you have any copper and silver nitrate laying around in your Christmas trees. What's polymerization? You know what a polymer is? Not video, but it's. You have polymerization. Think of this like in when we make synthetics. So a lot of the stuff that we have in our homes and stuff that's dangerous to us, it's formed. You have your simple molecule. Okay, now it's joined under a force to make into like. I'm not doing a very good job here. Let me try this again. There's your one. Join them and made a new substance. So you think about, you take like a hydrocarbon and we use those to make things like plastics. That has to undergo polymerization. I'm gonna show you a video, and then we'll talk about how that applies to hazmat. So this will just kind of give you an overview.
You're not dreaming about rain right now, but these tiny crystals, known as pellets, are the chief component in making a wide array of plastic and is the end result of polymerization. You might be wondering, what is polymerization? Well, polymerization starts when a catalyst meets with a basic molecule to make longer, more complex particles by the breaking of double bonds. And the process of creating these repeating structural units are known as polymerization.
Okay, what's a catalyst?
Material that elicits a chemical reaction.
It helps that, speeds that up. Okay.
The origins of polymers comes from reservoirs of oil and natural gas being pumped, piped, and refined into side products and byproducts. This is ultimately where feedstock comes from, which is the first step in polymerizing plastics. And the feedstock then goes into a steam cracker, where steam is used to heat furnaces to break down the feedstock into their base parts through a maze of blazing hot pipes. It is then cooled into a dense liquid-like gas where it is then separated out into ethylene, propylene, butadiene, and cracked benzene. It is then sent to their assigned tanks where it awaits to be used. Once it's determined what type of plastic or polymer is going to be made, the monomer gas is preheated and ushered into the molecular sieve where water and other contaminants are filtered out by a material called zeolites. The dry gas is now ready to interact with the heart of the system, and that's the stirred gas reactor, where polymerization is continuously carried out, where propylene, ethylene, and hydrogen are introduced to the reactor. Solid catalyst is introduced to the reactor to kickstart the formation of polymers. While this is happening, a lot of heat is created, which is unfavorable in polymer formation. So this heat needs to be dissipated. The unreacted monomer is recycled, cooled, and compressed, and then pumped back into the system to regulate the temperature. And this ensures that the monomer can be polymerized to specifications. Once the polymer is made, it is removed from the reactor through dipping tubes, where the polymer goes through the polymer gas separation process. This starts with carrier gas, where steam and additive are infused with the polymer to deactivate the catalyst. The product is then filled into a discharge vessel where unreacted monomer is recovered. When all the unreacted monomer is extracted, the polymer is then pumped out and goes into the purge vessel, where a single axis stir will mix nitrogen, which is pumped into the purge vessel. Nitrogen helps stabilize the polymer and removes any moisture and volatile materials. The nitrogen is also used to propel the powder to the powder silo, where it awaits its last leg, the extrusion and mixing process. This starts by feeding the plastic material along with water and additive through a hopper into a barrel of the extruder. The polymer powder is gradually melted by the mechanical energy generated by the turning of the screw. Excess water and off-gas is removed via vacuum port, and the molten polymer is forced into an underwater cutting die. This is to cool and shape the pellets. The pellets are then driven into a centrifugal dryer where water is separated from the pellets. The pellets are transferred to a series of mixing silos for storage purposes, while air is integrated into the mixing silos to recirculate the pellets to prevent clumping and to facilitate the packing of the final product. And this is how polymerization is done in a gas phase reactor. Thank you so much for watching. Please like and
So
subscribe.
just an overview. So when is this a problem for us?
there's a lot of materials being mixed together that.
Yeah, so you can have a high quantity. So we've got a chemical reaction. So we've gone from our monomer, which is the single. And then now we're joining them all together. So you have a chemical reaction to make this chain. And what do we have when we have a chemical reaction? What's produced?
Heat.
Heat, yeah. And so sometimes these happen so fast that it produces a lot of heat, which becomes a problem for us. A lot of these substances, they are given an inhibitor. Okay, so that's added to it. And what do you think an inhibitor is?
A anti-reactant or it's
So something that's gonna slow that down, right? So the opposite of a catalyst. And so sometimes something happens, so maybe that inhibitor is it's changed or it's taken out of that chemical through some or that material through a process, okay, whatever that is. And so then that can react easily. Okay, so then we have that rapid polymerization, which is a hard word to say, which generates a lot of heat and energy. That makes sense? Okay, questions about that? All right. So what's a catalyst? Yeah, so that increases the rate of polymerization. And what's an inhibitor? What's that?
Something that slows.
Slows it down. So it's gonna increase the needed activation energy. Okay, so shipments of polymerizing materials, they might become unstable if there's a delay, or if they're in an accident or anything like that. So what are we gonna do? Okay.
identify.
Yep. See, upwind, uphill, and yeah, always work. Right, hey, we're gonna take another 10-minute break. And then we'll be back here. And then we'll finish out till lunch. When we talk about acids and bases, we talk in terms of pH. Do you know what the pH of human body is? 7.35 to 7.45, which makes us basic. So I'm just saying I'm a basic girl. Okay, so acids are on a scale from 0 to 7, and then bases are from 7 to 14. So something with a pH of 0 is what? Yeah, and it's highly acidic. And then a base of 14 on the is very basic. So if you look in your book on page 144, they talk about different terms in when we're referring to acids and bases. So some people say acids are corrosive and bases are caustic, but when we're talking about the like the DOT, when it has the placard of 8, which is what? Corrosive, yeah. So that means that it can either be an acid or a base, because corrosive does what? Yeah, it'll destroy your tissues, and a base can do that, and an acid can do that. So in terms of like the DOT, then just consider that acids and bases are corrosive. Okay. Excuse me, sorry. Sometimes they refer to basic solutions as alkaline. So just know the different terms can mean the same thing. Okay, acids they're usually called acid. So we got hydrochloric acid, nitric acid, sulfuric acid. You guys ever gotten acid on yourselves? Hurts, right? A base, we talked about, has a 7.1 to 14. It breaks down the fatty tissues, and that's called saponification, which is also a term for making soap. Pretty gross. So, you might not know it right away, so it might take a little bit, and then, so if you're starting to get slick or greasy, or you have a patient with that, their tissues are being broken down. They've probably been exposed to that base. Okay, so we got caustic soda, potassium hydroxide, and other alkaline materials. They're described in strength and concentration. So your strength would be a weak or strong. Go ahead.
Sorry, it was about that last slide, so
Yeah.
like getting a slick or greasy patient, if you get some of that on you,
Yeah.
in that.
What would that be?
That'd be contamination,
What kind of contamination?
cross contamination.
Or?
Second.
Good. Okay, yeah, absolutely. So what do we want to do first?
Sure, you have,
Okay, you got PPE, and what do we want to do to the patient?
Decontaminate.
There we go. Okay. All right, but nope, good question. So we talk about something being a strong acid or a weak acid, strong base, or a weak base. So we look at the scale, so 0 is a strong or weak acid. Strong, okay. 14 is a strong or weak base, okay. So the strength is it is what it is. The concentration is like when you dilute it, like you can put it in water. I think of this as some of you might be too young, but you have a glass of tequila. Okay, drink it. It's strong and it burns going down, but you mix it with margarita mix. Okay. Put the tequila in there, and then it's diluted, right? And so then you can sip it all night long. Okay, what's the hazard of acids and bases?
Their caustic properties.
Corrosive. All right, flammability. So, as it says, flammable materials can damage life and property. They ignite, burn, or explode. I think that's pretty common sense. So we want to know how flammable the hazardous material is, right? All right, we talked about this. We're going to revisit it. What's flash point?
thing. You should like can.
Do you want to tell us again?
Flashpoint is the point at which a substance can ignite but not sustain a reaction.
Okay, good. So then, what about fire point? You want to take a stab at it?
Say it's the same combustion. Or reaction.
So it is giving off enough vapors that it will sustain combustion. And not too much difference between the flash point and the fire point. All right, so here we go. You can have your flash point of gasoline, -45. Okay. Fire point is -40 to -35. Pretty broad range here. Boiling point of gasoline, 90 to 400. And typically it's like 100 and 125, I believe. And then the ignition temperature.
So is that the temperature of the gases? Or is that?
Yeah.
Okay.
Okay. So, what's auto ignition temperature?
Or does it need a heat too?
When it doesn't need what?
When it doesn't need like outside, yeah, that's what it does.
Okay. All right. Self-sustained combustion without initiation from an independent ignition source. Okay. So auto ignition is also known as spontaneous. And those are gonna be a lot higher than your fire flash point. All right, so we have our LEL and LFL, the lower explosive limit and the lower flammable limit. So that's the lowest concentration that it will burn. So if the temperature is below that, I'm sorry. If the concentration is below the lower explosive or lower flammable, then it's too lean to burn. Okay. That makes sense? All right. Now, on the other side, you have the upper explosive limit or the upper flammability limit. Concentrations above that, it's too rich to burn. Have you guys are familiar with that term? So in between those levels though, it'll readily burn. So say, when you think about a substance, so you've got something that is in this range. What do you think is more dangerous to you? So you have a wide range here in your concentration, so it will burn anywhere in here. For this one, will burn in.
It has a wider range.
Wider range. Yeah. So that is more hazardous to us.
Doesn't that partially depend on the temperature though? Because it could be a wide range, but if it's like 300 degrees to 500 degrees, I mean.
Yeah.
Normal.
Just playing with. But when are we gonna see things? Oh, no one is 300 degrees.
Yeah.
All right. Just as a disclaimer, concentrations above the UEL do not guarantee safety. Okay, here are some of your flammable ranges. What do you think?
Acetylene is very flammable.
Got a pretty broad flammable range. Okay, so here's kind of a picture. So it looks like he's got some WD-40. Here's our ignition source. Coming here, so this is too rich. The concentration is too high. And so then it comes out here, and then all of this is our flammable range. And then here, the concentration is too lean to burn. Okay. That picture kind of make sense there. Aerosol. Suspension of fine solid particles or liquid droplets in air or another gas. There's several terms a few pages back. Probably want to take a look at those. On page 130. But where that comes to play first, any flammable or combustible liquid, when it's aerosolized, it could ignite at temperatures before the listed flash point, fire point, or auto ignition temperature. All right, so we are going to move on to page 148. Talk about radioactivity, we're gonna get a little more into this later on. Bless you. What hazard classes, radioactivity, radioactivity? 7, okay. So you wanna, what, and how do we recognize what's the symbol?
A trifoil.
The trifoil, yeah, okay. So need to be able to identify those and just need to know, basic protective strategies. We've got, non-ionizing radiation and ionizing radiation. So non-ionizing has the, is the least energetic form, where ionizing is the most energetic and therefore the most hazardous. This is in your book on page 148. So it talks about like different things. So on the non-ionizing, so low. So some different ways. Your infrared, microwave, radio, and then you have ionizing. X-rays, ultraviolet, gamma rays. And then effects. So you can have some non-thermal, so not too much of an issue there. Thermal, which is heat there, and then on the ionizing, we have broken bonds, skin damage, anything. Okay, and so down here, you look at all the different sources. Excuse me. Okay, 4 different types, but alpha, beta, gamma, and neutron. So these are the different levels here. So alpha is going to stop by your skin. Beta stopped by clothing. And then gamma is going to it's going to go into your body, and then neutron is just going to go all the way through. So we got. All right, I'm gonna pause though, because I need to get it. Okay, so levels of radiation, and so continuing on 148. So an alpha, I'm so sorry. Alpha particles are they're very energetic, but they are stopped by your skin. But what can be a problem is if they're ingested or inhaled. So the beta, fast moving, those are emitted from the atom's nucleus during radioactive decay. They can penetrate the skin, causing more damage. And again, more so if they're inhaled or ingested. And then gamma radiation, high energy photons. They can, like we talked about, they can go in, go through the skin easily. And then with the neutrons, it's not listed in here, but it's in your book. So just know that your PPE does not protect you from gamma radiation. Where are we going to find these? Hospitals, medical facilities, maybe some labs. We're more likely to encounter them here than in maybe some other areas. Is not sufficient against neutron radiation. I believe this has been on the test before, so radioactive materials, RAM. How likely are we to encounter radioactive as HazMat incident? What are we more likely to encounter?
Contamination. Radioactive.
Yeah, there's that, but as far as hazardous materials incidents.
Flammable liquids.
Okay, good. There's always the concern of radioactive materials used in what would what type of hazmat incident would that be considered? What do we call it when hazardous materials are used as weapons?
Oh, don't give them that.
Weapons of mass destruction. Okay, and then again, what's the difference between exposure and contamination?
Exposure is like when it gets like inside of, like, you breathe it in, or, you know, it gets into your body, and contamination's like just, it's not, it doesn't go.
What do you think? You guys agree with that, or do you think it's the opposite? Okay, think back to our awareness, difference between exposure and contamination.
Exposure is only gets into and emissions when it's.
And what's acute?
Sure.
Chronic?
Over a long period of time. And cancer.
So typically the chronic exposure is small doses over a long period of time. Body can deal with better than an acute exposure. You know, see here it says unlikely first responders would encounter dangerous or lethal doses at a terrorist event. I don't think this is telling you not to take precautions. We have the radiation detectors here. Let's see if I can pull those out. We have a plan in place. So have you guys heard the time, distance, and shielding? So decrease your amount of time in areas with radiation. Maintain your distance and then create a barrier. Page 153, talks about the inverse square law. Doubling your distance from radiation divides the dose by a factor of 4. You know this term? Alora, as low as reasonably achievable. Great. How likely are you to encounter radiation hazards?
Low.
Yeah, pretty low. More so out here. Just if you ruin it. Excuse me. Gosh. We're actually making really good progress on our stuff here. So before we go into our next section here, let's take the next the next 20 minutes. You guys can review